So I want to do one other thing in this first lecture. Which is to go to consider the most, in some ways, the most general scenario where any welfare guarantees are known for any sort of non-brute force procedure. And it's going to illustrate a nice trick for how you can prove price of anarchy bounds for Bayes-Nash equilibria without going through the smoothness regime. So it's going to be a more direct argument, which seems necessary for a result of this generality. So let me tell you the setting. I think we're at scenario 9, but to be honest, I've sort of lost track. So this is going to be the most general one we've seen thus far, where bidders have what are called subadditive valuations. Which just means that if you look at two bundles, then my value for their union is at most as much as my value for each of them separately. Okay, the sum of my value for each of them separately. So you should be wondering how this relates to all of the other classes of valuations that we've seen. And the answer is, for the stuff we've been focusing on, this is strictly more general than anything we've studied thus far. So in particular, it's not hard to prove, I'll leave this as an optional exercise, that this is strictly more general than XOS valuations. So XOS valuations, that was this sort of perhaps weird class, this maximum of additive valuations. But the key point was XOS was strictly more general than submodular. And remember, submodular was already giving us sort of, fits for multiple weeks, okay? So the picture you want to have in mind is gross substitutes, that's sort of the frontier of tractability, as we've discussed, of exact tractability, at least. Then we went to submodular, and we studied that for a long time. And now in the context of these simple auction formats, it turned out that was the important property of submodular valuations for simultaneous second price auctions at least, was that they're a special case of an XOS valuation maximum of additive. And then subadditive is out here, okay? And all of these are strict. So for example, showing containment is quite easy. So suppose you have an XOS valuation. Why is it subadditive? Well, okay, so suppose your evaluation was actually additive, right? And think about S&T disjoint. That's the interesting case here. This holds with equality, right, for an additive valuation by definition. So suppose your XOS, well, just pick the additive valuation that's exact on this particular bundle. And that's going to give you some lower bound on the valuations over here. But then re-optimizing, picking the new additive valuation to maximize this, and to maximize this will give you something only higher. Okay? So that's kind of the two-line proof of why XOS has to be subadditive. And it's not hard to find a strict separation either. All right? So what else should you know about subadditive valuations? There's no known sort of constant factor DSIC mechanisms or anything like that for subadditive valuations. The good news is if you just look at the algorithmic problem of welfare maximization, we do know how to do that well in polynomial time. Well meaning there's a two approximation algorithm. It's an ingenious approximation algorithm. Okay, so it's not easy, and it's from, it's a little less than 10 years old, so it's relatively recent, but we do know how to do it, okay, assuming demand oracles, okay? And the way you should sort of think about subadditive valuations, I mean, it's basically, roughly the frontier at which we know how to do constant factor approximations, even if we don't care about incentives at all. So in some sense, it's the limit where we might hope to have constant factor guarantees for simple auctions. Okay? And as I'll show you, you can get that. Okay? That'll be the point of the rest of the lecture. Okay. All right, so good. So you have to work hard to develop a polynomial time algorithm to get constant factor approximation. What happens if you just use some simple auction like simultaneous first or second price auctions? Okay, that's the question. So fact is that smoothness doesn't seem to get you a constant factor. At least as to the extent that we understand the limits of smoothness. So it seems to get stuck at giving you a price of anarchy at like 1 over log m, where m is the number of items. And the reason that you pick up a log m going from, so remember, we do know how to get a constant factor here. That was the point of the last couple weeks. And the reason you pick up a log m going from XOS to subadditive is the XOS valuations had this really nice property that, so remember, it was always how do you define the B stars? How do you define the deviations? And the way we did it is we said, well, let's think about what items we rightfully are supposed to get in the optimal solution, and then we're going to go all out for them. And in our analysis, we really used 2 properties, right? We used that there was this additive valuation, so this bid, that was exactly representing our valuation on this particular set, and was only smaller on every other set. So only underestimated, so didn't overbid on other subsets. And if you go back and look at the analysis, I don't expect you to remember offhand, but we really needed both of those properties in verifying the smoothness inequalities. And those bids just don't exist for subadditive valuations. To target a set and with an additive valuation, so or with bids in a simultaneous single item auction, if you want to bid exactly your value on a particular subset, you might be forced to overbid on certain subsets by a log factor. Okay? And that logarithmic factor shows up in the analysis. Okay? And it can cause you problems. So you can get a 1 over log price of anarchy, but it's not known how to do better using these extension theorems. So instead what we're going to do is we're going to use a direct argument, and I'll tell you what I mean by that. And it still sort of has the flavor of smoothness, but it isn't. But the good news is the bottom line looks really good. Okay, for simultaneous first price auctions, the Bayes-Nash price of anarchy, and this has to be product distributions. Remember, we know even for unit demand valuations, the correlated price of anarchy is terrible. But for product distributions, we get that this is bounded below by 1/2. And so again, this is the best we know how to do with arbitrarily sophisticated polynomial time approximation algorithms. So it's competitive with approximation algorithms. Sort of apples versus oranges comparison, but still, that's something we're very happy with at this level of generality. And then for second price auctions, it degrades down to a 1/4, but it's still a constant factor. Okay? So I'm going to show you this proof. I'm going to show you this result. This is similar arguments, a few extra details. Okay, so this is going to be the plan. All right, so what does it mean to go beyond smoothness, to do a direct argument? So here's the flexibility we're going to allow ourselves in the proof that will allow us to get these better bounds. Okay. So idea, we're still going to be defining these hypothetical deviations, B star, but in smoothness, within smoothness arguments, the key point is that they're independent of whatever bid profile B we're eventually going to invoke it in. Okay, so the order of the quantifiers were for every valuation profile, there exists B stars, so that for every B. Okay? So the difference now is we're going to allow our B stars to depend on that B. Okay? So, if we go all the way back to our very initial price of anarchy analyses, this is sort of like saying, well, look, this game might have multiple equilibria. All I want to do is prove every single one is good. So why can't I just, for each equilibria separately, pick my own favorite hypothetical deviations that prove that this particular equilibrium is good? So that's enough to prove that all equilibria are near optimal. It's just never how we've been doing it. We've always been exhibiting these deviations without first looking at what equilibrium we're talking about. Okay, so we have sort of a uniform choice in all of our previous analyses, a uniform choice of the deviations B star, that we use those for every single equilibrium. And we're not going to do that. Okay, now we're going to look at the equilibrium and say, oh, for this equilibrium, I'm going to deviate this way. to show that this one is good. For this other equilibrium, I'm going to deviate this other way to show that this one is good. And I'll show a generic way to do that that handles every single equilibrium. Okay, and that's good enough. If all we care about is to prove that all equilibria are near optimal, this is fine. It's not a smoothness proof. There aren't going to be any extension theorems, but the proofs won't look that different than the extension theorems either. Okay, so that's what's different. Okay, so an equilibrium specific deviations rather than equilibrium agnostic deviations. Okay. All right. So let me show you the key nugget of this analysis, which is really quite cute. So key lemma, and this is also where we really use the subadditive assumption. So remember, we're talking about simultaneous first price auctions. So fix a bidder I with its subadditive valuation VI. And here's the important part. Fix a distribution D on the bids by the other players. Okay? So there's n items, there's m items, there's n players. B minus I, remember what this is? This is n minus 1 different m vectors. Okay? So these are distributions of what other players are doing. Now in the proof, in the eventual proof, this distribution is just going to be what other players' actions at an equilibrium. Okay, so we're going to look at some Bayes-Nash equilibrium. Other players will be bidding in some random way, and that'll induce some distribution. Okay, so that's how we're going to be a client of this. But for now, just there's some distribution on other players' behavior. Fix a set S. And so now, there exists a B star I. And so notice, right, I've seen this distribution. So again, equate this distribution D with some Bayes-Nash equilibrium. I've seen the distribution first, and only now am I showing you the deviations B star. Okay, so that's the sense in which this is a direct argument rather than a smoothness proof. So then there exists a B star. This is going to be a function both of this distribution D and the set S. That you should think of S as what we're targeting. So that's going to be like a bundle in some optimal allocation. And then, okay, so what's going to be true? What's going to be true is that we can lower bound our expected utility with respect to this distribution. Okay. So remember, B star I, this is not random. This is some fixed bid that we're doing as player I. This is something random. We're looking at our expected utility. And we claim that the expected utility is going to be at least half of our value for the set that we're targeting, minus an error term. Okay. So this is just the expected sum of the highest bids on the set S that we're targeting. Okay. So is the lemma statement clear? Like I said, the proof is a cute symmetry argument. Okay. Good. And then basically, looking ahead, when we prove the price of anarchy bound, we'll just use this instead of a smoothness condition. Okay, this will sort of substitute for a smoothness condition. All right, so enough to show. All right, so we're going to use the probabilistic method. We're supposed to exhibit some fixed B star I that meets this inequality. I'm going to just pick B star I at random from a certain distribution. And in expectation, this inequality will be satisfied. So by averaging, there exists some choice of B star I that satisfies the inequality. So enough to show a random B star I works in expectation. So here's how I'm going to randomly choose this deviation B star I, okay, so that this holds in expectation. So I'm going to basically mimic the other players, or rather I'm going to mimic the maximum bid of the other players. Okay, so there's n minus 1 players, so on any item there's some distribution over their bids, there's some distribution of the highest bid. Okay, so I'm just going to set my bid I'm going to have it be distributed on a given item in the same distribution as the highest bid by some other player. So specifically, choose sample. Okay, so there are echoes of the doppelganger trick here, although I'm not actually sampling a valuation, I'm just sampling an action. So remember, D is a distribution over bid vectors. So I sample, a typical bid vector that the other players are going to play. And then I set my deviating bid as follows. So, right, I'm targeting this set S. So we're going to be, we're only going to bid non-trivially on items of S. And what do we bid? We just bid the maximum bid according to A minus I. Okay? So the claim is this works. So is the deviation clear? So again, what I'm told is I'm told the distribution over other players' actions. Again, think of that as being in some Bayes-Nash equilibrium. I'm told a set of items that I'm targeting. Think of that as being some bundle in an optimal allocation. When I'm going to bid 0 outside of that, how do I bid on the items in S? I just say, well, let me sample what other players might be doing. I'm going to look at the highest bid by some other player, and I'm actually going to set that to be my bid. Okay, so I bid as if I'm a highest bidding player, highest other bidding player on an item. Okay? Okay, so, and this works. So in what sense does this work? So let's lower bound our utility. The way I'm going to lower bound our expected utility, where the expectation is now both over our random choice of B star I and over the random instantiation of B minus I. First, I'm going to say that our expected payment is at most this term, and that our expected welfare is at least this term. Okay? And that's good enough to lower bound my expected utility. Expected payment at most that, expected welfare at least that. All right, so with expected payment, if you can just keep all this in your head, is straightforward. So how much is bidder I going to pay when it picks B star I at random this way? Well, who knows, because we don't really know what's going to win, what's going to lose. But it's not going to pay more than it bids, right? If it wins everything it bids on, it'll pay exactly what it bids, and otherwise it'll pay less. So the expected payment is at most the expected bids. And so what's my expected bid on a given item J? Well, it's distributed exactly the same as this, just by definition. Okay? So by definition, right, so this is just literally how we set our B star ij, okay, for each item that we're bidding on, all right? And of course, I'm calling it A minus I here, I'm calling it B minus I here, but who cares, right? They're drawn from the same distribution. So this number and this number are the same, okay? So our expected payment is certainly no more than this. So how about the expected welfare? So now we're going to use the symmetry again. So by symmetry of B minus I and A minus I, so this is nice. So for a given subset of S, remember S, so there's some big set of items U, and then there's some set of items that we're targeting S. We're going to win some of them where we're the high bidder, and we're going to lose some of them where we're not the high bidder. So consider the probability that we win exactly the set A versus we win exactly the set of items S minus A. So what can you say about those two probabilities? Any guesses? What would be the best, what would be the coolest thing? All right, so these are equal. Okay? So why are they equal? Well, what happens? Okay? Okay, so what's the, I guess I should say, what's the probability over? All right, so the probability here is over both A minus I and B minus I. I should have specified that. Okay? So other players are bidding randomly, and so are we. Okay? All right, so we win the items where we're the highest bidder, and we lose the items where we're not the highest bidder. Okay? So if we win the set A, then it means the following property. It means for the items J that are in A, it means the maximum entry, so the maximum bid on J in A minus I, our bid. Okay? So what are we bidding? We're bidding the maximum entry in A minus I on the item J. Okay? So if our entry is bigger than the biggest of the entries on J and B minus I, then we win. Otherwise, we lose. Right? So if we win the items in A, that means that A was exact. So that means in the realization of A minus I and B minus I, A were exactly the items J, where the highest entry in A minus I was bigger than the highest entry in B minus I. A minus I and B minus I have exactly the same distribution. So it's just as equally likely that what we're calling B minus I could have been our A minus I, and simultaneously what was our A minus I could have been the actual B minus I. That is, it's equally likely that the other bidders, the highest other bidder would be what we just bid, and what we just bid was the highest other bidder. And if we swap them, then we're just winning S minus A instead of A. Okay? So for each pairing of A minus A and B minus A, just swapping which way it goes, you exchange between winning A and S minus A for some A. Okay? So just integrating over everything, you still get this. All right? So that's good. So that uses just, our clever choice of this randomized bid. It doesn't use subadditivity. So now let's use subadditivity to say, so remember what we're trying to do. So we've already upper bounded our payment and expectation. Now we want to lower bound our welfare and expectation. So I is expected welfare. Is, well, let's look at all the sets that might win. A times its value for A. Now what I want to do is in this sum, which is ranging over all subsets of A, I just want to pair up A and S minus A. Okay? Because I know they have the same probability. That's what we just argued. Right? So, just in S, let's have some distinguished element 1. Okay? So choose an item 1 in S. This is just to break symmetry. This is just so that for any A, I count exactly one of A or S minus A exactly once, and I count the other one 0 times. Okay, so I'm just pairing up A's and their complements. Okay, so let's just sum over subsets that contain a distinguished element. And now, so what I've done, I've just grouped the terms together corresponding to A and S minus A. So this is now VI of A plus VI of its complement within S. Okay, so again, this is just pairing up A and S minus A for every A in this sum. And remember, these are the same for A or S minus A, so that's legit. So now I can use subadditivity. Okay? So the sum of its values for each of these bundles separately is at least as large as its value for all of the set S. Okay. Actually, let me then pull this out. This is now independent of A. And so because we got this by just pairing up things with equal probability, this is going to be equal to a half. Or if you prefer, this is just the probability that you win a particular item 1. Again, by the symmetry argument, the way we're bidding, we're going to win a given item exactly half the time. Okay. All right. And so that proves the key lemma. All right. And so so a couple things. So again, all right, so this is the key part of the proof which really doesn't seem to have an analog, which is really sort of beyond smoothness in a formal sense. So again, smoothness inequalities, we flip the quantifiers, okay, in the sense that the deviation B star depends on D, which corresponds to some equilibrium, okay? And if you look at this proof, I mean, it's really unclear how you'd have a version of this proof which was oblivious to the distribution D. I mean, it uses it, you know, in a very fundamental way, it seems, right? These symmetry arguments. So that's very clever, all right? And like I said, this key lemma will substitute for a smoothness condition in the price of anarchy proof, which is what I'm going to do next, okay? All right, any questions about this? All right, so, good. Yeah, so the proof that's coming up, it's, you know, it's a little bit technical, like the doppelganger tricks that we saw before, but then, you know, then we'll be done with the lecture, and then we'll take a break and have an easy second lecture, okay? All right, so, all right, so again, what we want to prove is that simultaneous first price auction, arbitrary product distribution over subadditive valuations, Bayes-Nash equilibria within a factor 4 of optimal. Okay? First price auction, so we don't expect to need any no overbidding condition. Okay? Actually, a factor 2, excuse me, factor 2. All right, so the first maneuvers will be familiar. So consider a Bayes-Nash equilibrium. In first price auctions, remember there's this nice optimization we can do where we can basically cancel the error term we get at the end, which are just the winning bids. We can cancel that with the revenue on the left-hand side. Let me remind you what that is. So what do we actually care about? What we actually care about is the welfare of the equilibrium. But always in these price of anarchy of auction proofs, we pass to player utilities because that's what the equilibrium condition's about. So we have some of the utilities plus the revenue is left over. Okay. So this is just by definition. Eventually, we'll be able to cancel this revenue term with, you know, that final error term we always get, the sum of the winning bids at equilibrium. All right, so let's analyze this, right? Because this is where the equilibrium hypothesis can be used. And as usual, what we want to do is we want to lower bound this. And we're going to do that by considering hypothetical deviations. And instead of a smoothness condition, the key lemma will propose to us hypothetical deviations, which this time will be a function of the particular sigma that we chose. Okay? Now, okay, right, so let me define the deviation. Okay. So consider the situation where bidder I finds itself having the subadditive valuation V sub I. And moreover, right, and we're dealing with this Bayes-Nash equilibrium sigma. All right, so here's what it does. Okay, so to motivate the first step, let's look at this key lemma. So this key lemma tells us how to bid. If we know how other bidders are bidding, that's not a problem because we know the Bayes-Nash equilibrium. So we know what that is. But also this was for a particular set S. So it told us, you know, given a set S that we want to target, how to bid for that set. And canonically, we're now used to thinking of this set as, you know, the stuff you get in an optimal solution. But now we have the same problem we had before, where we needed the doppelganger trick, right? Where when a player I is sort of reasoning about deviations, it only knows its valuation, it doesn't know others, so it doesn't know the optimal allocation. So we need to somehow, in defining this deviation, pluck from thin air a suitable set of items to bid on, and we're going to do that the same way we did before. Okay, bidder I is just going to sort of hallucinate some doppelganger types, W, and then it's going to say, okay, well, for all I know, other players have these valuations, that gives me an optimal allocation, that tells me a bundle to bid on. Okay? So, here's the randomized algorithm defining the deviation for bidder I. So it samples the doppelganger types from the public prior F. I'm going to use F star I to denote the bundle I gets in the optimal allocation. The optimal allocation when this is the type profile. Now that I know a set and that I know a distribution on those bidders, now I can invoke the key lemma to figure out what I should do. Okay? So bid B star I, where this is a function of what my value is. It's a function of the types I've hallucinated for the other bidders, and it's a function of the particular Bayes-Nash equilibrium we're looking at. This, of course, defines a distribution over bids by the other players. Okay? So remember, sigma is known. Sigma is the mapping from valuations to bids. We have a prior on V, so we know a distribution over V minus I. We know sigma, so this is a distribution over B minus I. Okay? So sigma minus I, V minus I is exactly a capital D. Okay? So this is just the distribution of the bids by the others. That's a capital D. So as in key lemma. And so in the key lemma, we take S to be S star I, VI, W minus I. And we take D to just be sigma minus I, V minus I, where V minus I is drawn from the known prior. Okay? All right. So if a bidder really, really wanted to, it could act in this way. Okay? And its utility we know would only go down. I should say this is also a recent result. So this is a stock, this result is a stock 13 paper, Feldman, Gravin, and Lucier. Okay, so for every bidder, for every type VI it might have, since sigma is a Bayes-Nash equilibrium, its utility only drops. So the randomness is, let me write this out. So its equilibrium utility is bounded below by its utility if it acted in this way. So let's just expand out the randomness in the actions of player I. Right, so we have randomness in what other players' types are. We have randomness in bidder I's action. It picks a W. And then it does this bid, B star I, which depends on all this stuff. Right, so that's what it's doing. Others bid according to the Bayes-Nash equilibrium. And now we apply the key lemma. All right, so for the key lemma, what I want you to do is I want you to think of W as fixed. Okay, so remember, V are the actual player types. Okay, W exists only in the mind of player I when it's trying to figure out how to bid. Okay, so and how does it use W? It computes the optimal allocation and it figures out this bundle of items it's getting S star I in the optimal allocation. So think of W as fixed, and at that point then the set S that bidder I is bidding on is fixed. Okay? At that point, we apply the key lemma, okay, for a fixed W. And we apply it to this thing, okay? So the key lemma gives us a lower bound on how well we're doing with this deviating bid. And what do we get? We get half the value of the set that we're targeting. Minus the expected highest bid on the items that we're targeting, where now the expectation is over the uncertainty in other players' types. Okay? Okay, so this is B minus I drawn from D. That for us is just the equilibrium bids by the other players. Okay? So sum J in S star I. And then we just look at the highest bid by somebody else, and the bids are just given by the Bayes-Nash equilibrium. Okay? So the notation here is this is K's type, sigma K of VK is its bid given its type, and remember a bid is an M vector, and here I'm looking at item J, so I'm looking at the jth component of that M vector. Okay? All right. And so now the rest of the proof looks similar to when we first did the doppelganger trick, okay? So this was all reasoning about a fixed player I who knew its valuation V sub I. So now we're going to integrate out over V sub I, so average over player I's type, and then sum over the bidders, okay? All right, so what do we get? Well, on the left-hand side, we get the expected sum of player utilities. So what do we get on the right-hand side? Well, something nice happens, okay? In particular, this term is nice. All right, so let's stare at this for a second. So remember, think of W as fixed for starters. So, okay, we're integrating out with, okay, so what is this? So this is the welfare I contributes to the optimal allocation when its valuation is VI and everyone else's valuations are W minus I, okay, just by definition. So it's a contribution to the optimal welfare in that situation. Now integrate out over W, okay, average over the types W minus I that other players could have, okay? So what's that? That's just the expected contribution of player I to the optimal welfare when its type is VI. And I don't know anything else about other people, okay? As W minus I varies, I'm contributing something to the optimal allocation, and then if I average out, that's just how much I contribute to expected optimal welfare when I'm VI, okay? So now if I integrate that out over VI, that's just my expected contribution to the welfare, okay? So once I integrate out over VI, this just becomes I's share of the optimal welfare. Okay, so that's great. All right, so the first term is exactly what we want. Well, I guess there's a 1/2 there. So 1/2 expectation over V of opt V. All right, so we declare victory on that term. Now what about this term? What about this term? Okay, so we're integrating out with respect to VI, so a VI joins its compatriots, V minus I, and we're also summing over I. Let me write this in the following way. I'll put the sum over bidders first and then the expectation. And then I'm just going to copy the sum again. All right, and this is simple but sneaky. What happens next? All right, so this, I haven't done anything, okay? I just wrote down what we had before and reorganized the sums. So here's the sneaky part. I claim I can change this to WI. Okay? And it doesn't matter. So why is that true? Well, let's look at what we're talking. Okay, what is this? What are we talking about here? So this is the highest bid by some player other than I. Okay? In the equilibrium. So this doesn't depend on I at all. Okay, I has nothing to do with this. It doesn't depend on I's type. Okay, I's actions are not involved. All right? So doing something with player I has no effect on this thing. So the only thing that could matter is if it somehow affects how things were distributed, but it doesn't. Right? So how is VI, W minus I distributed? You know, remember, it's a product distribution. So this is just a random valuation profile. WI, W minus I is also just a random valuation profile. Okay, doesn't matter. Either way, this is just the set that I gets in a random valuation profile. Okay, doesn't matter. So this number is exactly the same, either way. Okay, so let me replace this by just W. Now, why does it matter? Why is it nice having this be sort of a bona fide, kind of coherent valuation profile that's independent of I? Well, here's why. So push this sum. God, I love linearity of expectations. I love it so much. When I teach 161, it's the only time, that's the algorithms class, it's the only time all quarter I put something in a box. I write it down and I put it in the box. And I say, this will be on the exam. It's the only thing I do that for. All right, so push the sum back in here. Okay? So now, so inside the expectation, what do we have? Sum over I. Sum over the items in the bundle that I get in the optimal allocation. And then we have, again, the maximum bids by others at equilibrium. The point is, now that this is just some fixed valuation profile W, as I range over I, these optimal bundles are just a partition of the items. Right? So over a fixed W, these are valuation profiles. The optimal allocation is whatever it is. And so as I sum over the bidders and I sum over the items the bidders get in that optimal allocation, I just sum over all the items once, each. That's it. Okay? So in other words, this, right, so equals just sum over J and U, right? So this just ranges over every item once. Max equilibrium bid. Okay. Right, and I guess to get rid of I, let me just do this. So make this equal. So I'm just going to go ahead and throw I back in. That'll only make this bigger. And now this is exactly equal to the revenue term over here. Okay. So that was true W by W, so I can integrate out over W. And so, need another color. So the upshot is this is at most sum over all these of sum over I equal 1 to n. So these, remember it's a first price auction, so these are just the payments that people are making. So pi of sigma of v. Okay? So this gets canceled out with this. So putting all together, we get that the expected welfare of the Bayes-Nash equilibrium is lower bounded by this half of the welfare. Okay? So that's it. So again, as far as the high level, the details of these last few lines are slightly different than the doppelganger proof that we saw. But again, if you had to do it yourself, you could figure out all these tricks. So as far as what's sort of the new idea here, the new idea here is really the key lemma. The new idea here is really to recognize the additional flexibility, the additional power you have by choosing deviations as a function of the Bayes-Nash equilibrium. A priori, because you have no idea what the Bayes-Nash equilibrium looks like, it's not clear how to use that knowledge in your proof. And so here the really cool idea is, well, I don't know what it is, but it's some distribution, and I can sample from the distribution in my deviation. And at least for subadditive valuations, the symmetry between this sort of battle between you pretending like you're the other bidders and the other bidders themselves is enough to give you this factor 2, combined with all of the other ideas in our toolbox. Okay. All right, so let's resume at 4, and we'll talk about revenue maximization for, I promise, at most an hour. Okay. And it'll be mostly examples, so it won't be too. It'll be good for a late afternoon lecture.